Welcome back to Carneades.org. Today we're going to be doing the complete video of the philosophy of outer space. Today we're going to be diving into the philosophy of outer space. Now, often when philosophers talk about the philosophy of space, they mean space in the metaphysical sense, the three dimensions that we live in. However, there are also important philosophical questions to be answered about outer space, the parts of space that are not Earth. Some of these questions are for science, but they do have philosophical implications, like whether or not there's life on other planets. Some of them are ethical questions that fall clearly into the realm of philosophy. How should we interact with aliens if we encounter them? Others are epistemic questions for the philosophy of science, like whether the methods we use to study outer space are actually epistemically justified, given that we can't actually perform tests on the vast majority of the universe. Others still fall in between various components of science, philosophy, and religion, like how did the universe start? Are there multiple universes or just one? In this video, we're going to cover all these questions and more. The Earth makes up at most only a very small percentage of the matter in the universe, but this is the subject of the vast majority of philosophy. Let's today take a second to talk about the other 99.9999999, etc. percent. So, first we're going to start with the Fermi Paradox. So, are we alone? The first question for us to tackle is perhaps the earliest question that one might ask upon looking up into the night sky. Are we alone in the universe? Now, there are a range of ways that this question can be approached. One might argue that the universe is insanely vast, and therefore there must be other life out there somewhere. Basically, this is the intuition behind the claim that if you get enough monkeys and enough typewriters, they'll eventually write the complete works of William Shakespeare. The universe seems very vast, even just looking at it from the Earth. The more we study it, the larger and larger it seems to be, to the point of possibly even being infinite. It seems like with such a large amount of space and a large number of planets, there have to be other planets that have been able to support life. However, on the contrary, there are elements of life that seem so unique and so hard to reproduce that despite the gigantic size of the universe, it's not likely that life has emerged anywhere else. Even if someone can assess how big the universe is, they're going to struggle to determine the likelihood of life, let alone intelligent life emerging, because those are processes that take hundreds and thousands of years to happen. And so we have this problem of we have a huge number of possible places life could emerge, but also a very low likelihood of the actual processes of life happening. So, one might also argue that this is a question for science and not philosophy at all. If you give science enough time, they can look at all the planets and just see if there's life on them. But this once again runs into the problem of just how vast the universe is. Not only does this size make it difficult to travel to the planets and check for life, it makes it hard to even be confident that we have looked at enough planets to be sure there is no life anywhere. We can't even observe most of the universe. This is especially true since the visible part of the universe is very small, if not infinitesimally small compared to the rest of the universe. Also, epistemically, it's very hard for science to prove that something does not exist. Even if you did check every single planet, it would be tough to say that there is absolutely no life anywhere else in the universe using inductive methods, and so we may need some deductive philosophy to bring to bear on it. Even if we use science to figure out what planets would be suitable for life like ours, then only check those for signs of life, we have the problem that life might look very different on other planets. Even if we are successful at eliminating the possibility for life that looks very much like us, it may be impossible for us to be assured that life which looks very different, which is perhaps not even based in matter, but based in energy only, or based on very different kinds of elements and molecules and existent in very different environments, thriving under very different conditions, doesn't exist, because those could be the very conditions that are inimical to our life and that we couldn't even go into to check if we wanted to. Now, in from this comes Enrico Fermi. A different way to approach this question comes from the Fermi Paradox. The paradox can be framed in a range of different ways, but here's one of them. There are and have been many potentially habitable planets that could develop life. We see this when we look up at the stars. There are many planets that seem to be in the position or have the correct elements such that life might be possible. Earth is not the youngest of such planets, so life should probably have developed somewhere else, given that we are not the first of such planets to exist. There are other planets that could support life, many, many other planets that could support life that have been around longer. If life developed somewhere else, then we should see evidence of it somewhere. Maybe probes sent to Earth, structures on distant planets, electromagnetic waves, or even a radio signal at all. But we don't see any evidence of other life. In other words, where is everybody? Let's look at each of these premises in turn. So, there are other planets that could sustain life. As with anything in the universe, this is hard to estimate and even harder to know with certainty. However, scientists estimate that there are tens of billions of Earth-like planets in the Milky Way galaxy alone, and there are hundreds of billions of galaxies. Based on this, it seems that there are many other planets with the same conditions to sustain life. Next, Earth is not the youngest or the first planet that could fit these descriptions. Scientists have evidence, based on the age of the universe, that Earth is not the first planet to be able to sustain life. It is not as if this were a common process and we were just the first to be on a planet that could support life, since there have been billions of other planets, many of which are younger than Earth, which could have, and so if they followed a similar process, should have supported life. Therefore, we should see some evidence of galactic civilizations. If there was life on other planets, we should see some evidence of it. Radio waves on Earth have only been transmitting for a short period of time, but have already traversed over 100 light years in space. Even if a society died off long ago, we should be getting echoes of their existence as they became able to transmit information. We would also think that a powerful enough society would soon start to occupy other planets, would expand throughout the galaxy, and would eventually expand throughout the universe, such that we would start to see physical evidence of their presence. Even if that society died off, we should see the relics that they created, the existing radio waves that are broadcasting through space. We should see pieces of that society, even if it existed long ago. But we don't see any evidence yet of aliens. Setting aside conspiracy theories, we don't yet have any real evidence of life elsewhere in the universe. We certainly don't have evidence of a big galactic civilization that's coming to conquer all the planets in the solar system or put an intergalactic highway through planet Earth. We seem to be the only ones putting out messages into space. Despite doing a lot of work to listen very closely to the stars, we have never heard anything, much less observed physical evidence of other societies. Now, there's an interesting parallel to this, which is the question of where are all the time travelers? So, a quick aside, there's a corollary to the Fermi paradox for time travel, which simply asks, if backwards time travel is possible, where are all the time travelers? Most works of speculative fiction that include time travel need to have some explanation for this. Perhaps time travel is not possible to years prior to the year that time travel was invented. Perhaps time travel creates a new branch of the universe, and you can only travel backwards along that new branch, not to the original main timeline. Perhaps time travelers have visited, in fact, but there are enough rules or technology that prevent them from being noticed or interfering with our time. Well, it's an interesting corollary to the Fermi paradox, and some of the solutions may have either isomorphic similarities, such as the zoo, or the same solution can solve both, such as the simulation. A full treatment of the philosophy of time and time travel is going to need to await another video. The first of these solutions that we'll look into is called the Great Filter. So, the question here is, what stopped the galactic empire? Life, as we understand it, likes to spread, to replicate, to make more of itself in every possible crack and crevice it can find. So it makes sense that, provided with sufficient time, it would spread beyond its own planet. This is a slight variation on the Fermi paradox, as it asks not just why we haven't seen any evidence of any life elsewhere, but why have we not seen a galactic civilization, a civilization that exists on all planets in a galaxy? One explanation for this paradox is offered by Robert Hanson and is sometimes called the Great Filter. This argues that there is some stage at the process of achieving galactic domination that is very, very hard to overcome. That even if there are many situations where the conditions of life are right, or the conditions are right for intelligence, or the conditions are right for civilization, that there is at least one stage in that process somewhere that is so hard to overcome that even if there are billions upon billions of possible places it could happen, it rarely happens, and it may have only happened once. Hansen puts forward 9 steps on the journey to galactic colonization, any of which could be the very unlikely one that limits the billions of planets that could support life to so few we have never yet seen any that have achieved galactic dominance. This question then becomes, is this great filter behind us, implying that humankind is the 1 in a trillion civilization that made it through? Or in front of us, meaning that there are other civilizations out there that have reached our level or gotten close to our level, but there's some great filter in front of us that is going to mean we face a full extinction or some actual barrier to complete galactic conquest. Let's take a look at the filters. So, the first step is something we can test for to a certain degree. Does a planet have the right conditions for life to form? We do observe many planets with such conditions. Now, we can only observe so many conditions about a planet, and we can only understand its environment to a certain degree. We can understand how far away from it is it from particular stars in a particular habitable zone, perhaps what elements are present within the solar system that we're looking at, but there are some conditions that we perhaps can't understand. Maybe there are particular features of our planet that made it ripe for life that we're unable to observe in distant planets. And so we may be overestimating the number of planets out there that have the right conditions for life. A commonly supposed place for the Great Filter is at the stage of what's called abiogenesis. This is the question of how we go from chemistry to biology. How do we go from individual chemical reactions that do not self-replicate themselves into a self-replicating process? A full discussion of abiogenesis deserves another video, but scientists think that the conditions of the early Earth were such that the necessary lipids, proteins, and RNA were able to form and given millions of years and trillions of individual molecules, eventually one of them formed a self-replicating cell. However, this is a rare thing to happen. We have not been able to reproduce abiogenesis, and so this could be the great filter that we're looking for. The next step up from just self-replicating RNA is supposed to be prokaryotes, which look like our modern bacteria. This is sometimes combined with the previous step, as some suppose that you would need the conditions of a modern prokaryote for abiogenesis to happen, while others argue that we might have had much simpler cells when life first started before millions of years of evolution made bacteria more complex. Eukaryotes are more complicated cells that are found in animals and plants. These cells have within them organelles which make the work of producing energy much more efficient. It is supposed that these eukaryotes evolved through a symbiotic relationship between mitochondria, an organelle that in many ways resembles a prokaryote. They have their own DNA, etc., and the larger eukaryote, perhaps eating but not completely digesting it, perhaps developing, kind of going from a parasitic to a symbiotic relationship, we're not sure. This is another stage that is often supposed as the great filter, since such a symbiotic relationship developing, which had such a substantial boost for productivity for the eukaryote cell, may be unlikely. The next potential filter, according to Hansen, is moving from asexual reproduction of a single cell dividing itself to sexual reproduction. Sexual reproduction gives greater opportunity for variation that can lead to evolution, since it means that cells are not relying solely on mutations to change DNA, but can have greater diversity in populations and therefore greater opportunities for beneficial changes. And even cells can select their potential future mates based on particular characteristics such that they have a better ability to evolve and replicate those beneficial characteristics. Another step in the process is moving from single-celled organisms to multicellular organisms. Some suspect that this may have taken place when a group of single-celled organisms grouped together and then began to specialize and gained benefits from this specialization. A rare enough instance that this may be the great filter itself. The next supposed step is that we need animals who have cognitive functions sophisticated enough that they can use tools. Brains are evolutionarily costly things, and while they pay off in the long run, it may have been just luck that we evolved with them, and that they were actually able to stick around long enough for us to really put them to use. The next step is planetary dominance. This is often framed as the stage that we are in now, moving from using tools to being the dominant form of life on the planet, capable of manipulating other life forms to our own will. Because we don't know exactly what the next step in the process is, we don't know what about our current stage is crucial. What about it might be considered a great filter? Perhaps it's industrialization, perhaps it's farming, perhaps it's something else we haven't gotten to yet in terms of technology. There could be components that are necessary and others that are superfluous to whatever is needed to take that next step. The next step, once we've conquered our own planet, according to many theorists, is galactic dominance, colonizing other planets and spreading throughout the solar system. Unfortunately, we don't know what that next filter will be because we haven't made it past them yet, nor do we know if the great filter actually lies behind us or if it lies ahead, perhaps at the step of moving to other planets, or maybe it's moving outside of our own solar system. Maybe species can colonize a solar system, but then there's some filter out there that we haven't realized yet that stops them from going beyond their solar system, or perhaps leads them to collapse completely. Now, there's some concerns with this idea of the great filter. First, it might be the case that there is no one great filter, but actually many individual smaller filters. As much as narratively it's interesting if there's one great filter that's cutting us off, it could be possible that simply combining a bunch of very unlikely instances leads to us having an unlikely probability. It could be that every step in this process is unlikely on its own. There's no one that is impossibly unlikely. It's only when they're put together that they become so monumentally unlikely we find ourselves as the only life we can see. Second, in the other direction, even if it is the case that there is a great filter behind us, that doesn't imply that there's not also a great filter in front of us. Even if we are the only ones to ever get this far, it's possible that the next step is even harder, if not impossible. A third concern could be raised is whether all forms of life would really strive for galactic dominance. Maybe it's not a filter that kills us off in front of us, but some change in values or ideals that leaves all societies to not attempt to go out and conquer the galaxy in some way. Or maybe many forms of life do evolve, but those forms of life look very different than our form and don't try to populate all the planets. There are other concerns that could be raised. We might worry that there is not just one path that life could move down, and that there may be many other galactically dominant species we don't even recognize because they are so different. We might think that we are not, in fact, close to the final step in the process, that there are many more steps before us. And even if there is not a future great filter out there, there may be many small filters that could stop us, similar to the possibility of many small filters behind us. Next, let's take a look at another answer to the Fermi paradox, sometimes called the zoo. So, also called the prime directive. Another explanation of the Fermi paradox is often described as the zoo, but it can be explained easily through the Star Trek prime directive. This is the idea that there may be some set of rules out there that prevent advanced societies from communicating with societies that are not sufficiently advanced yet. Perhaps these societies are able to hide themselves from our observation, or are even required to by galactic laws. Perhaps their technology is something that we can't even detect or see. In this case, we are in the zoo. There's some point in the future where we will graduate out of the zoo if we become advanced enough. Maybe that means sufficiently advanced space travel, or the discovery of a new type of communication system that would mean we can actually detect communications from these super advanced societies that we previously couldn't detect. Perhaps that means we need to evolve to a certain new form of life that would be able to engage with these societies. Fiction has imagined a range of ways that we could discover this and first encounter new alien species. We could also be the seed of a life planted by a large, very distant civilization which expands throughout the universe by placing pockets of life, then leaving them alone to grow, or protecting them from the rest of the universe. This is a bit of a combination of this one and another answer to this theory, but it's a possible a possibility we could understand, that perhaps we are that seed of life that was placed here as a very small, maybe the great filter is at the level of abiogenesis, and the species just placed us here as prokaryotes or eukaryotes to eventually populate the planet, and is purposefully leaving us alone to see how we evolve. Who knows? Now, there's some objections to the zoo theory. One concern with this explanation is that it becomes less and less likely as science becomes more advanced. Every scientific discovery that we make without discovering aliens makes it less likely that we will discover aliens with a future discovery. There are more sensors. The more sensors we create and find nothing, the harder it is for us to justify the belief that there are aliens that are progressively better and better at hiding. This theory makes a lot more sense in the 1800s than it does today. Even if there are strong regulations against it, most laws and regulations in our society are bent, if not outright broken. So it seems unlikely that we would have no information about such people, unless aliens are just much better at enforcing such laws. Just look at how many times Starfleet ships accidentally interact with such pre-warp civilizations to get a sense of why there's at least some questions here. Next up, in terms of responses to the Fermi paradox, we have the simulation. So this is something that philosophers, particularly in epistemology, know well, and skeptics like myself. Another response to Fermi's paradox is to simply say that maybe we're in the matrix, or something that is sometimes referred to as an ancestor simulation by scientists. The reason that we do not see any other species that have evolved on other planets is that we're not actually on a planet at all, but we're in a computer simulation. There are several reasons we might think that this is the case. If we imagine a sufficiently powerful civilization that wants to live over and over again and extend their life in different times and different places, we can conceive of them constructing a gigantic simulation where everything is fake. You might be a member of this civilization right now, but when you die, you simply wake up and perhaps enter another simulation, living hundreds of lives throughout your life. As video games and movies become more and more immersive, it's not hard to imagine how such a society might be created in a few thousand years, especially given that 1,000 years ago, our society was much, much more primitive. In fact, if this is a simulation, we're already creating simulations inside of it in the form of video games. We might conceivably already be several layers down within a simulation within a simulation. This would explain why there's nothing out there in space, simply because we didn't create anything out there for this simulation. Our simulation might be modeled after the real world, or it could be completely different than what the real world exists like 1, 2, or many levels above us within a simulation. Now, there are some objections to this explanation. One concern with this explanation is the claim that it would take monumental amount of computing power to simulate the entire universe, something that would be impossible to contain on Earth. Now, there are a couple of issues with this objection. First, it relies on a model where the simulation is recreating the entire universe. Practically, the simulation would only need to simulate anything that the people in the simulation were actually interacting with at a given time. It's rare for folks to interact with molecules anywhere other than planet Earth, and most of the molecules in planet Earth are on the inside, and we're not interacting with them on a daily basis. And one does not need to simulate them all to create the appearance of the sky whenever needed. Anyone that has looked at how objects far away in video games are poorly rendered can imagine how a simulation would not really need to simulate exactly everything, but rather just things that people in the simulation are actively interacting with. Another objection to this explanation is that such a reality would make most knowledge impossible. Knowledge, by philosophical definition, requires statements to be true. If we're in a simulation, any statements about the world are false. In fact, even the rules of math or logic could be different in the real world. However, this objection commits the fallacy of necessitation. Just because we want to have knowledge doesn't mean that we can actually have it. Doing so would beg the question against the skeptic. This explanation does raise more questions than it answers. We would know nothing about the real world. We would not know if we are 1 level down in a simulation, or 2 levels down, or even many more. But as a skeptic, if anything, it's a comforting possibility that when we die, we'll just wake up and discover that our whole life was simply a game, and that there are many more games we can play. Another solution to the Fermi paradox is about communications. So, Another possible explanation is that aliens have been communicating with us. We're just really bad at interpreting it. Perhaps what we take for background radiation is actually aliens on other worlds working very hard to communicate with us. This potential diversity of life may be hard to imagine. It might be hard to imagine that what we would conceive of as communication would look very different from what another society would conceive of as communication. But this potential diversity of method of communication can be very hard to conceive of. There could be beings that communicate very quickly or very slowly at such rates that it might take lifetimes for us to understand them, or we might pick them up as a single blip on a monitor. They could be communicating at a very different scale, very large or very small compared to what we do. And so we may not be picking them up because we're expecting something at our scale, either in terms of time or space, and we're capturing something very different. However, there are issues with this explanation. While it might explain why we haven't received communication from other aliens, it doesn't explain why there's not yet an intergalactic civilization. It also doesn't explain why life like us has not evolved elsewhere. Even if there is a range of diversity of life in the universe, why has life that at least somewhat resembles us not appeared elsewhere? Others claim that communications do importantly look different from natural phenomenon, regardless of the culture that you're coming from or the species that is evolved in a particular place. One can think of the Voyager record or the Pioneer plaque to compare. It's hard to imagine how an alien race encountering such creations would think of them as anything other than being made by an intelligent being with the attempt to communicate, even if they were not able to fully understand them. However, this may simply be a failure of our imagination. Perhaps the other life out in the universe doesn't even use physical objects in the same way that we do. Now, another answer to this problem is intelligent design. So, without digging too far into the philosophy of religion, it is worth noting that one of the explanations for the Fermi paradox is intelligent design. Basically, the claim that one of the steps in the great filter is impossible to overcome without an all-powerful, all-knowing being guiding things. Proponents of such claim that therefore such a being must exist. Abiogenesis is a common step that is proposed for this theory because it seems like a particularly challenging thing to get over without it. Now, there are a range of concerns with this claim. First, it just pushes the problem up a step. If we're concerned about the improbability of human life showing up without a creator, we should be even more concerned about a likelihood of an infinitely more powerful being showing up without a creator itself. The second issue is that it does not do everything that the theists think it does. Aliens could be the creatures that guided our development. Life could have been seeded on this planet billions of years ago. That doesn't imply that it was your particular version of a particular deity that did it, or even a deity at all. Check out our videos on the teleological argument for the existence of God for more on these back and forth. Next up, related to this, let's talk about the ethics of galactic colonization. So, all of this raises some interesting challenges when it comes to the questions of whether we should do things like sterilize probes, rovers, and other craft that we send into space. Right now we do. Right now we try to eliminate any life that is on an object that we're sending into space. On the one hand, we care about learning if life has evolved on other planets. If it has, we don't want to contaminate life with the life that we have here on Earth. This is something like the zoo theory. We don't want to bring life to a place that it isn't. Some of this is driven by concerns that folks have with the way that different plants and animals have spread on Earth when humans have brought them to new continents. They have become invasive species in different ways. They become invasive, they can destroy natural life, etc. In other words, if the Great Filter is in front of us and there's a lot of life on other planets, we don't want to damage or destroy it. However, there is another argument. Imagine instead that the Great Filter is behind us, that we are the only species that has made it this far. Maybe the issue is abiogenesis, and nowhere else in the universe does any life exist. If that is the case, then we have the opportunity, if not the responsibility, to spread life throughout the galaxy. And we should be shooting extremophiles, life that can survive even in space, at every planet we can imagine. Because there is a good chance that we will mess up our own planet. There's a good chance that the only way that life will be able to get off the planet is if we help it. And we help it before we destroy ourselves. If the Great Filter is far enough behind us, then it was not unlikely that sentient life evolved from basic bacteria, but it's very unlikely that life started at all. If we want life to continue to exist, we should be doing everything we can to send it to every planet we can. Humans might not be able to get off this planet, but that doesn't mean that life can't. And we may be the only ones that are able to ensure that life continues to exist. Now, part of the issue here is time horizons. It took a very long time for us to reach each stage of the ladder described by the Great Filter. In our science fiction, we imagine that the processes of galactic domination is fast, that we will be terraforming Mars any day now. Some of this is for the same reason that cults who think the end of the world is coming always set the date within the near future, because they want to be relevant, because they want their short lives to be meaningful. But this might not be the case. It might actually take a huge monumental amount of time for this to happen. And the first step in that process might be sending bacteria to these other planets to get things started, because they may be the necessary precursors to getting plant life there, to eventually getting animal life there, to eventually getting intelligent life there. This terraforming process may take thousands, if not millions of years, and we may need to be doing it as soon as possible to set up perhaps not us, but perhaps a future evolved species to live. What if the terraforming takes centuries, and the first step is sending out microbes and getting them established? What if it is not humans that will survive to take over the cosmos, but the creatures that evolve from the microbes we send into the universe? What if the one thing stopping us is our desire for knowledge of whether there is other life, instead of our preference for helping life to expand? The original thought experiment claims that life always tries to find more nooks and crannies to grow, but we're not doing that with the probes that we send out into space. But maybe that's another great filter in front of us. Maybe once a society becomes able to get into space, there's some desire to keep space clean that prevents them from expanding until it's too late, until they've used up their own planet's resources to be able to leave the planet or destroyed it. Now, this raises some very thorny ethical questions. What is our responsibility to life itself? Not just other humans, other animals, but the very possibility of living matter. Do we have a duty to help life continue on the universe if we're truly alone? And what is our responsibility to life on other planets? Do we risk infecting them if we spread the life we have? Or would they benefit from receiving more diverse life there, from understanding themselves that they are not alone? One of the key challenges with these questions is an epistemic one. What are the risks and what are the chances of each scenario? What are the odds that we are the only life in the universe? If they are high, if it's a high chance that the Great Filter is behind us, there seems to be a very good case for sending out extremophile organisms that can survive anywhere to ensure that we don't destroy our universe's only chance at life. By sterilizing our rovers, we could be dooming all life in the universe. But on the other hand, if there's a high likelihood that the life exists somewhere else and the Great Filter of some kind is in front of us, we could be doing great harm by sending what could become an invasive species or a new plague to another world. There's also the question of the size of the impact. Would the possibility of wiping out an entire planet with some microorganism be worth the benefit of possibly avoiding the complete extermination of all life in the universe, when we inevitably destroy our planet because we were too risk-averse to send life somewhere else, or when we simply collapse as a species and the life on our planet dies off when our planet is destroyed because we were the only ones that could have sent life somewhere else, because we were the only ones that were able to come up with any type of space travel. It's a thorny ethical question. Should we risk the possibility of losing all life in the universe at the risk of possibly creating a plague somewhere else that would destroy another planet? Last but not least, before we leave the inner part of our solar system, we have a question of the treatment of aliens, which connects to this ethical question. Should we make love or war? So a closely related ethical question to whether or not we should be spreading life throughout the galaxy is, what should we do if we actually encounter alien life? Should we embrace them or should we fight them? Should we hide from them or should we try to communicate from them? There are several factors that might lead us into leaning one way or another, and plenty of speculative fiction that can point us in one direction or another, in situations where people try to talk to the aliens destroy us, or people don't try to talk to the aliens, try to fight them, and the aliens were trying to be peaceful all along. We don't know. First, what if we encounter very basic life, something microscopic? We might be interested in studying it to understand how it's different from us or similar. We likely would want to contain it, at least it cause a pandemic or disease on our planet, or that we cause it particular harm. We'd probably also want to protect it from us and our diseases so it didn't lead to extinction. Experience of humans and other species coming into contact with each other after a long time apart has led to disastrous consequences in our past. There seems to be an ethical reason to preserve such life, such very basic life, both to expand our understanding, but also in case it provides some benefit to humans in the future. But we probably want to preserve that life in a very contained and quarantined environment, least we cause more problems either for it or for ourselves. The next question would be, what should we do if we encounter a civilization that is similarly advanced to our own? Perhaps they are very different from us, but they have a similar level of technology. Should we fight them or try to make peace? Some understanding of this can come from political philosophy. It likely depends on their political structure. Democracies effectively never make war with other democracies, at least in our history. If they have such a system of government, then trying to make peace and trade with them is likely a good option. If they have a much more authoritarian structure, then war and conflict are more likely, so a stronger stance would probably be more effective. Learning about them and understanding the other society is an important precursor to making a decision of how we should deal with them. Though, depending on when they show up or how we find them, we may not have that opportunity. Now, we can take some lessons from game theory, particularly the iterated prisoner's dilemma. Check out our video on that for more. Consistently, the most effective strategy in the iterated prisoner's dilemma is something called tit for tat, starting with cooperation and then replicating the action of the other party. So assuming we have no information about what they're going to do, starting by trying to cooperate, and then if they attack us, attacking them back. This might be an effective strategy with another civilization on par with our own. Start with cooperation, but if they attack, respond in kind. We should also think about the principle of proportional response in war. If we are attacked, responding in kind to avoid a misunderstanding spiraling into a galactic war. What then if we encounter a more advanced civilization? Likely they would encounter us before we encountered them. They would probably visit us at home. It's hard to imagine what such a civilization would be like. We think that we have become more moral over time, that we've become more ethical. So perhaps we would hope that a more advanced civilization would be more moral even than we are now. However, perhaps our morals have held us back from technological advancements, and the society we meet will be bellicose and violent and try to take us for slaves or destroy us completely. In such a situation, we might be best served by gaining information or intelligence about the other society as soon as we can. The more we know, the better we can inform our response. Translation may be challenging, a set of philosophical problems in itself. There's likely not a single right response that would work in all situations, so getting as much information as we can to inform the decisions would be crucial. But it's also important to note that this, dealing with a more advanced civilization, is more a tactical problem than an ethical one. Since they are the more powerful society, they would therefore bear more of the ethical burden in how they act towards us, whereas our response is more around the tactics of how would we survive this interaction, as opposed to trying to figure out what the most ethical way to deal with them is. Next, we're going to dive into cosmology. So, cosmology is the science of the universe. As we move outside of the asteroid belt, we shift from the FMY Paradox to the philosophy of cosmology, the science of the universe. Cosmology is quite a complex field, and the goal of this part of the video is not to explain all of cosmology, or even to explain all of the philosophy of cosmology, merely to give an introduction to the subject and to talk through some crucial philosophical issues that arise. Now, cosmology has its biggest impact for philosophy in the areas of philosophy of science. Are the methods of cosmology really science or just pseudoscience, something more like philosophy itself? Philosophy of religion, how did the universe begin and how likely was it to begin? And metaphysics, are there multiple universes that exist, and is a real infinity actually possible? We'll look at all of these questions here. But first, a little bit of background. Cosmologists observe the universe by looking at the light and other electromagnetic waves that reach our planet. These allow us to look both far in terms of distance as well as backwards in terms of time, because light takes time to reach us. The further away something is, the further back in time we are looking. Cosmologists then develop models for the universe and see if the observations that we see match the predictions of those models. Sometimes cosmologists posit unobserved entities like dark matter or dark energy to explain phenomena that don't quite fit their model or observations. Now, cosmology is a particularly unique field for a range of reasons. Most subjects of scientific inquiry are the kinds of things that can be experimented on. They have multiple things that they can study and survey using statistics to increase our level of confidence. Cosmology is unique because there's only one universe that we can observe, and the vast majority of it is something we cannot run any experiments on. And we're only observing from one point in space and from a very limited point in time. There is so much space and there is so much time, and we only have a very, very small sample. The current paradigm for cosmology is the Standard Model, which uses what we observe about gravity and other forces locally to extrapolate conclusions about what the universe is doing as a whole. This model requires assuming the existence of dark matter and dark energy to explain why we don't observe as much matter or energy in the universe as we would expect. In order to do cosmology, we need to make some big assumptions. Specifically, we need to assume something called the cosmological principle. We need to assume that the part of the universe that we can interact with is a fair sample of the entire universe. In other words, that the laws of the universe in general make up the universe in other parts is the same as what we see here. This applies to both experiments done on Earth, as well as the behavior of cosmic objects within the observable universe being the same as those outside of the observable universe. Cosmologists need to do this to do cosmology, and at all, since we cannot actually test the conditions on the other side of the universe. As we will see, this raises some epistemic concerns. With that, let's talk about some of the problems with cosmology. Now, there are a lot of issues with the Standard Model that signify we might be due for a paradigm shift. Dark matter and dark energy are some of them. These are things that, particularly dark matter, is something we cannot observe, but must be there to make our theories work. These have a clear parallel in the shift away from classical mechanics to what we now include as our paradigm around physics. Our classical theories could not explain the perihelion in Mercury's orbit. Initially, instead of changing our paradigm away from classical mechanics, we posited an unobserved planet named Vulcan that was between Mercury and the Sun. It turned out there was never such a planet. Our theories were wrong. Similarly, needing to posit things like large amounts of dark energy or dark matter in the universe to make our equations work doesn't necessarily, but may indicate that the problem isn't that there's a bunch of stuff that we can't observe, but that our equations are actually wrong. Now, falsifiability. One of the biggest issues with cosmology from a philosophy of science standpoint is that it isn't really science. Karl Popper argued that the claims of science must be falsifiable. However, the claims of cosmology, particularly the cosmological principles themselves, are not falsifiable. We need to assume that the universe is uniform at a sufficiently large scale to draw conclusions about faraway locations, but we can never actually go to those locations to test if these conclusions are true. If they're false, we can't do cosmology. If other parts of the universe look drastically different, follow very different laws from what we see on Earth, we can't really test that, and we can't test those other parts of the universe to figure out what laws they follow. One might suspect that it would be strange for our corner of the universe to be different, statistically speaking. Why is the one place we can observe from look different? The odds of our specific corner of the universe being one way and everywhere else being another are very low. However, there are a few problems with this framing. First, as any statistician will tell you, even if you have a truly random sample, a random sample of one place is insufficient to be representative of the whole. Second, even if most of the universe acts like the area around Earth, it doesn't imply that it all does. Even if it's unlikely that we are in a weird pocket of the universe, it doesn't mean that those pockets don't exist. Third, it is possible that the universe is not at all uniform, that there is no normal part, that every part has its own rules and its own laws. And it's not strange that our part has one set of rules, because every part has drastically different rules. Cosmologists commit the fallacy of necessitation here. They assume these principles because they're the only way to do cosmology. If they were false, we couldn't know anything about the other parts of the universe, since they might follow different laws. Beyond questions of falsifiability, cosmology suffers from the problem of induction, but in reverse. For any science to function, we must assume that the future is like the past. In other words, that our observations in the past will continue to hold in the future. Cosmologists must assume an inverse principle, that the past behaved like the present. Cosmologists draw conclusions about the past by looking at very far away objects, because light takes us a long time to reach us. The further away they look, the further back into the past they claim they can observe. However, often they are observing much further into the past than humans have ever existed or been able to observe things. However, just as this would only work if our location in space follows the same rules as other locations, this also only works if the rules have never changed in the past. If the laws of physics were different in the past, then all of the conclusions we think we can draw from looking at light that is just now arriving might be invalid, since that light might not be as old as we think it is, or it might simply be behaving under different rules because other parts of the galaxy might have different rules from what we have now, or other points in time might have had different rules. Our interpretation might be based on laws which did not apply when it was created. The problem is that there's no way to prove this true without time travel of some kind. It could be that the laws of the universe changed drastically at some point in the past. In fact, under current theories, cosmologists must assume something called cosmic inflation, which requires objects moving faster than the speed of light, which would break one of the rules that they need to assume in order to conclude it. Now, sometimes cosmologists argue that these theories can at least be verified by looking at something called the cosmic microwave background radiation, the radiation that we see from the first moment that the universe became transparent. The problem is that this still faces issues of underdetermination. While specific theories can be supported or not given a certain paradigm, the entire paradigm itself is much harder to verify, since there are many other paradigms that could explain the same observations. And without the ability to go far into the universe to test these theories empirically, at a certain point we're overfitting the theories to the limited data we have. If the only thing we really have to test things again is this cosmic microwave background radiation, then at a certain point we're going to create theories based around that to overfit the data, and perhaps not actually be doing anything that's testable because we don't have new data that's coming in. Very quickly as an aside on philosophy of science versus science. So, before a bunch of cosmologists get too frustrated in the comments, it's important to note and remember that there's a difference between science and philosophy of science. It is science's job to use the scientific method to test claims based on that method. It is the job of philosophy of science to determine which situations the scientific method can be validly applied to and whether or not a given situation is actually using the scientific method appropriately. Philosophy invented science, and it's the job of philosophers to determine what is and is not science. Because science doesn't study knowledge, philosophy does. Science doesn't study truth, philosophy does. Science doesn't study the scientific method itself, philosophy does. Therefore, it's fully within the purview of philosophy to question whether or not cosmology is really a science. Note that philosophers are not questioning, does cosmology say X, but rather, are claims made by cosmology justified? You might think of this like the difference between philosophy of religion and theology. It's the job of theologists to determine what a holy book says. It's the job of philosophers to determine if the claim that whatever the holy book says is true is actually justified. Philosophy is the discipline in which other disciplines swim. This is why everyone still gets PhDs, doctorates in philosophy, because everything used to be philosophy. All right, moving on. The Big Bang. In the beginning, so if we do allow these underpinning assumptions, cosmology can provide us with hypotheses about the origins of the universe, sometimes called the Big Bang. This has philosophical implications as it approaches an answer to the question of how the universe began, what the limits of our knowledge are, and much more. We will very briefly and simply explain the current timeline according to cosmologists. Now, The first question is an epistemic one. How can we possibly claim to know what the universe looked like when it started, which, according to scientists, was over 13 billion years ago, when humans can't even agree on the facts of our own planet, even a short time in the past? Is evolution true? Did we really land on the moon? Who did we say was supposed to pick up the kids this afternoon? Etc. The first thing to understand is that this model is that light takes time to get somewhere. Light takes just over 8 minutes to get from the sun to the Earth. To get from here to Saturn, it takes just under an hour and a half. This means that the further away you look, the further in the past you're looking. Because the distances in space are so large, this means that you can actually look a long way into the past. Light from Proxima Centauri, the nearest solar system, is from around 4 years ago, meaning we are seeing it as it was 4 years ago. Light from the center of the Milky Way is around 26,000 years old, so we are observing the center of the galaxy as it was about the time that some of the early instances of human pottery were created. The nearest small galaxy, the large Magellanic Cloud, is 179,000 light years away, meaning we're looking at it as it was when humans first started wearing clothes. We're seeing the nearest large galaxy, the Andromeda Galaxy, as it was 2.5 million years ago, how it was before we had gone from prokaryotes to eukaryotes. Perhaps this is an explanation of the Fermi paradox right here. Perhaps there are many other civilizations that are existing in other galaxies, but we just haven't gotten the message yet because it takes so long for light to travel from those galaxies here. Okay, so we can look back in time by looking really long distances, but how do we tell what those galaxies are doing? Whether or not they are moving away from us or towards us, etc. Cosmologists use something called the Doppler effect. Now, you've likely experienced the Doppler effect with an ambulance. As the siren gets closer to you, it seems increasingly high-pitched, but then it moves away and it gets lower-pitched. This is because the sound waves are getting bunched up as the thing emitting them moves towards you, making them higher-pitched, and they're more spread out as the thing moves away, making them lower-pitched. When this happens with electromagnetic waves, including light, the light shifts blue when it's getting closer, and it shifts red when it's getting further away. Atoms emit certain, very specific wavelengths of light, so when we observe distant stars, the red shift or the blue shift can tell us quickly that they are moving towards us or away from us. When cosmologists observe that the universe is expanding because all the galaxies have a red shift, it also appears that expansion is speeding up because the further away a galaxy is, the faster it is going, even accounting for the additional time it takes for that light to get to us. Space is getting less dense. This is also what leads us to think that there was no one origin point of the Big Bang. Galaxies on all sides of us are moving away at the same speed relative to their distance from us. So unless Earth really is the center of the universe is expanding uniformly everywhere. This is like if you drew a bunch of dots on a balloon and then inflated it. The dots are all spreading apart from each other. There's no one place on the balloon that is exploding outwards, but rather everything was close together and then everything is at the same time getting further apart from each other. Now, it's important to note that this expansion doesn't necessarily mean that the universe is getting bigger, just that it's getting less dense. If the universe is infinite, then it's not getting any bigger because it's still infinite. However, there is progressively more space in between objects. This is something like Hilbert's infinite hotel paradox, where guests in a full infinite hotel each move to a room that is twice the number of their original room, creating infinitely more vacancies. The universe stays infinite, it just gets more space in between. More on the implications of real infinities and Hilbert's hotel soon. Now, one key thing about that cosmologists point to when arguments about verifiability or falsifiability of cosmological hypotheses arise is the cosmic background microwave radiation. This is the radiation that we can see if a telescope is pointed out at empty space. It is predicted by the Big Bang theory, but it was not predicted by the competing steady state theory. because the prediction is that this microwave radiation emerged after the Big Bang when the universe cooled enough to become transparent. When it was first observed, that falsified the steady-state theory of the universe. These rays are the first light that was emitted by the universe when it first went from being completely opaque to being transparent. This radiation gives us a snapshot of the universe a few 100,000 years after the Big Bang. It depicts that the universe was much more dense and much hotter at that point. Based on this, the fact that the universe is expanding now, and experiments done at very high temperatures in the Large Hadron Collider, we can speculate about the events in the universe before this radiation was emitted. But the further back in time we go, the worse our understanding is and the less confidence we should have. All right, moving backwards from now. When we look back into the timeline of the universe, the past looks much hotter and denser than things are now. Note that this timeline is not to scale. So here is a brief glimpse at the timeline. Let's look at each of these pieces in order, starting from the current day. So our solar system was formed about 4.6 billion years ago. The Milky Way, our galaxy, was formed fairly early in the universe's history, about 13.6 billion years ago. Many galaxies formed during this period and have continued to form since. This epoch is often called the galaxy epoch. The first stars formed about 13.68 billion years ago. The first stars were formed as loose helium and hydron atoms collected together, ending the so-called dark ages as these stars started to light up and engage in fusion. Some of these stars go supernova at this point, creating elements that are higher up on the periodic table. There's a period called the Dark Ages that happens from the emission of the cosmic background radiation up until the first formation of the stars. It's from about 370,000 years after the Big Bang to about 100 million years after. The cosmic dark ages are a period after the universe was a giant, very hot and dense blob, up until when early hydrogen and helium atoms started to form up into stars. It began when the universe became transparent instead of opaque, and it's marked at its beginning by the release of the cosmic background radiation. So, as the temperature drops below around 4,000 degrees Kelvin, the universe suddenly becomes transparent. This is because all of the protons and neutrons start collecting up the electrons. The cosmic background radiation is released as the universe first becomes transparent, as electrons become bound to protons and photons are emitted all in one blast to the universe. This moment is often called decoupling. The cosmic background radiation is a snapshot of this point in time. Our evidence for what happened prior to this is much weaker. But we have some suppositions. We think before this we had a blob of quarks that coalesced into protons and neutrons as the universe cools about 1 second after the Big Bang. What we can guess about this time is drawn from experiments with particle accelerators that create very hot temperatures which mimic the early universe at this time. Some theorize that one of the different forces, such as the strong nuclear force, may have differentiated itself around this time, and that was what caused this shift. Now, before this period, we have a period of inflation. The universe is inflating rapidly, faster than the speed of light, very quickly growing inside, often called the inflationary period. Prior to this, we don't fully understand what's going on. We don't understand this because we don't understand how gravity and quantum forces interact with each other. Because in most cases, gravity acts on very large scales, and quantum forces act on very small scales, so we don't need to reconcile them. This is the point at which the universe, where things were so densely packed that we do need some kind of grand unifying theory that would explain how gravity and quantum forces are interacting with each other. We don't have one yet. Now, as noted, the further back we go, the less confident we can be. Even if we can reproduce these conditions in a lab, we can't know if the laws of physics would have operated in the same way in the early universe. There are also underdetermination issues all over the place, where many different hypotheses can explain the existing data that we have, making it challenging to determine what is correct. Some theorize that the Big Bang was the universe breaking off from another universe. Some claim it was the universe collapsing on itself and then expanding outwards again. Perhaps the universe has existed stably in a super hot, super dense state for a long time until one day something changed and it suddenly began expanding rapidly. Two more things to touch on about the standard model, dark matter. There are a range of questions that the present theories leave unanswered. One of them is dark matter. We see parts of the universe where light is being warped as if there were matter there that was exerting a gravitational pull. However, our systems, which can detect even matter which doesn't give off light, can't find anything there because it appears not to interact with light at all in this way. Some think dark matter is something left over from the formation of the universe, perhaps something that interacts with gravity but not with the other forces. Others think that it's another universe that's next to ours that's exerting influence. Others still think that our theories are just wrong, and just like the planet Vulcan, there's no such thing as dark matter, though this would likely require a paradigm shift to change our theories to account for these differences, just like we needed to change our theories to account for the perihelion in Mercury's orbit. Another concept that we're still trying to understand is sometimes called dark energy. This is the energy that is pulling the universe apart. We would think after the initial expansion, the pull of gravity would slow the universe down, possibly to a stop and possibly to even collapsing again. However, that's not what we're seeing. If anything, the universe is accelerating its expansion, though not as fast as it was in the inflationary period. Therefore, some have posited dark energy as a force that is driving the universe apart that we don't fully understand. As with dark matter, this could be described as something we do not observe, but need to exist for our formulas to work out right. So it's possible that it doesn't actually exist, and we're just misinterpreting the evidence we're getting from the cosmos, and we need new theories. Finally, some unjustifiable assumptions. While this is an interesting story, we might wonder if the evidence is sufficient to justify it. There are several tools that we're using to draw these conclusions, all of which rely on a range of assumptions. We'll look at several of these tools: looking back in time, redshifts, and cosmic background radiation. First, we have to claim that when you look into the sky, you're looking into the past. This faces the same objections as all of cosmology. Namely, it could be the case that there are different laws of physics in different parts of the universe, making light travel at different speeds than it does on or close to Earth. A similar case can be made against the idea of using redshift to assess movement of galaxies. It's possible that in other parts of the universe, chemicals give off slightly skewed spectra of information, or that there is some effect in between our galaxy and another one that's warping the light waves to make it appear that the galaxy is moving away, because it appears redder than it should be, when in fact it's some other phenomenon that's causing that, not a movement away, or not the same movement away we expect it to be. For the cosmic background radiation, this is often raised as a way that cosmology can actually act like a real science. Because it was predicted by the Big Bang Theory before it was discovered, this provides verification for this theory and falsification for its competitor. However, simply because it's consistent with the Big Bang Theory doesn't mean that this proves the theory, as there are many other theories that posit the same features of the universe. Okay. Now that we've talked a little bit about the science, let's talk about the religion and go into the cosmological argument. Something from nothing. So, a question which the Big Bang Theory does not address, though you might expect that it would, is how you get something from nothing. The key question of the cosmological argument for the existence of God. Now, while, as I argue in my series on the cosmological argument, the existence of God does not actually succeed in answering this question, it does ask an important question about how the universe began and why things are the way that they are instead of some other way. The Big Bang is consistent with many explanations of the origin of the universe, but it doesn't rule out a creator. It doesn't imply one or provide any evidence for one. It is possible the Big Bang was not even the beginning of our universe, but merely heralded a new stage in our universe. This is further evidence that cosmology suffers severely from the problem of underdetermination. There are many different theories that could explain the data, including the idea that God set off the Big Bang, but we can't distinguish between them. Note that some versions of the cosmological argument have more to do with possibility and necessity than kind of an initial temporal state. However, they are all focused on that initial moment of the universe. What caused the universe to be one way and not another? Next up, we're going to talk about a concept in cosmology called anthropic reasoning. This is the idea that we need to shift our expectations in terms of whether or not we have a biased sample. There are two key principles here, the Copernican principle and the anthropic principle. So, there are two principles used by cosmologists to estimate certain features of the universe. One is called the Copernican principle, which assumes that we are a normal observer. In other words, that we are not special and at a normal point in time and space. This is based on the claim that such special cases are rare, while the normal situation is much more common. We've noticed previously that some of the issues with this claim, the possibility that nowhere is fully normal, in other words, things look drastically different from every vantage point, the fact that this is just a fallacy of necessitation. If we don't assume this, we can't do cosmology, so of course cosmologists assert that it's true, and the possibility that our observations about the parameters are inaccurate. In other words, we are in a simulation, and the universe is actually much different than we think it is. But if that's not enough to make you doubt this absurd claim, here's a thought experiment. Imagine that you want to know what the opinions of everyone in New York City are about fashion, food, and music. You live in New York City, and according to the Copernican principle, you're likely an average individual. Therefore, whatever you think is what the typical New Yorker thinks. If you hate sushi, odds are everyone in New York hates sushi. If you love Weird Al, odds are everyone in New York does too, because you're probably a typical observer. If you wear shorts and a t-shirt to work every day, odds are that's what all New Yorkers do. It should be clear that this thought experiment leads us to a ridiculous conclusion. Just because one person picked out randomly is probably going to be in the middle of a distribution doesn't mean that they are going to be in the distribution or that they are representative of everyone in a population, especially when we're taking everything about that population as we are doing with the Earth, because that's the only point we can observe everything from. The problem here, as with the Copernican principle, is that a non-random sample of a single individual is never going to be representative. There's also evidence that cosmology is a pseudoscience. If the Copernican principle was false, we could never test it. We cannot observe the universe from anywhere but our little corner. And it's like someone doing an opinion survey without ever leaving their room by just thinking up what they think is true. Now, it's important to note, of course, we have sent telescopes and observation probes far out into our solar system and beyond, but even so, our solar system still counts as only a very, very, very small corner of the universe. Now, the other principle is the anthropic principle. This is the claim that the range of possibilities where we could find ourselves is limited by what we are, that there are certain points in time in the history of the universe where it's impossible to be a human observer. There are certain fundamental facts about the universe that, if they were different, humans would not exist. The anthropic principle argues we should take these into account when calculating our probability. Sometimes this anthropic principle is framed as having a weak version based around being required to be an observer on a planet that can sustain life, and a strong version that requires we are in a universe that can sustain life based on the cosmological constant and other constants within the universe. Another way of thinking of this is to say that this is a qualification of the Copernican principle. It says we should assume we are a typical observer out of the range of possible situations where an observer could exist. In other words, if the vast majority of places in the universe are such that they are inhospitable to life, we shouldn't assume that we are an average observer in any places in the universe, because most places in the universe do not admit of observers. We should assume that we are an average observer out of those places where observers could exist. This addresses issues that there could be a correlation between what we are observing and the fact that we are the type of thing that can observe. Such as if there's a particular type of gravity or interactions in areas that also happen to be better allowing of life. In other words, when calculating the likelihood of particular events, we should take into account the fact that simply by being an observer, we can only observe a subset of all events. One place this comes into play is when cosmologists calculate the push of dark energy to expanding the universe, the cosmological constant. Cosmologists calculate that the push of dark energy is very likely to be much greater than what we observe. This pushes against the Copernican principle, since it means that we're not in a normal situation, at least if our theories and calculations are correct. But the anthropic principle addresses this, since we are a normal observer, and universes with higher cosmological constants cannot have observers because they expand too fast for elements to combine and lead to situations where you could have life. So they argue that this is observation bias, because only in a universe with very little expansion due to dark energy could there be conditions that allow for life, and instead posit a near infinite multiverse to explain it, saying that there are many different universes, and we just happen to be in one of those universes that is allowing of life. This is once again a clear example of how cosmology isn't a real science. It is not falsifiable. The theory made predictions about the amount of energy and matter we would observe in the universe, and it was wrong. But instead of fixing the theory, instead of shifting our paradigm, cosmologists focus on positing more new, increasingly fantastical entities to explain more and more holes in the standard model of the universe by positing, oh no, let's talk about there being a multiverse. In fact, we're going to posit a very, very high number of universes to explain the fact that our numbers don't quite align up with what we're seeing in the world, instead of just admitting maybe our paradigm needs to shift. So there's some objections that we can have to this anthropic reasoning, the anthropic principle, and the Copernican principle. So these principles combine the worst of two separate yet both epistemically sketchy fields: cosmology, much of which is arguably pseudoscience, and Bayesian epistemology, which tries to codify the degrees of confidence in particular statements through conditional probability. This kind of probability especially has issues with dealing with first-person perceptions of events and how that can impact your probability assignments. Check out our video on the Sleeping Beauty paradox for more on how this idea of a first-person assignment of probability can differ from the real probability out there in the world. This conflation of the epistemic situation we may find ourselves in, of this is likely because of who we are, and the likelihood of it actually existing out in the world, leads to this shaky abductive reasoning that we see in cosmology. Now, there are a range of issues with these two claims together as well. First, they rely on identifying an observer class. While this may seem straightforward, it is anything but. We do not know all the possible shapes and forms that life can take. We have only ever seen one example of life. Once again, a sample of one is not sufficient to draw conclusions. So making claims based on any possible observer is nonsense, since you don't know what the parameters for a possible observer could be. There could be observers that could exist in universes that have much, much higher cosmological constants. They might be observers that are very, very different from what we look like, but that doesn't mean that they're impossible. Just because you can't imagine it doesn't mean it's impossible. Now, this does lead to another piece of philosophy of religion closely connected to cosmology, the fine-tuning argument. Once again, cosmology veers into philosophy of religion with an argument called the fine-tuning argument. This is an argument about the physics constants in the universe. We have a full series on the cosmic fine-tuning argument, so check that out if you're curious, but we will touch on it briefly here. So, the argument basically claims that there are several constants, specific numbers that are used throughout the universe, which, if they were even slightly different, would mean that life in the universe is impossible. The argument claims that the only way that we could be so lucky as to be living in a universe with constants so finely tuned to life would be if there is a creator of the universe that designed it that way. In some ways, the intuition behind this argument is the same intuition behind the cosmological argument itself. It is asking the infinite why. Why is X a certain way? We can explain complex structures in biology with chemistry, we can explain complex structures in chemistry with physics, but at a certain point, there are certain laws of physics that we cannot explain why they are a certain way. They simply are that way. This argument says that because we can't yet explain why these constants are a certain way and not another way, therefore they could have been different. This is getting at the underlying argument of the original cosmological argument, this traditional argument of asking how we can get something actual from something that is merely contingent. Why is the universe one way and not another way? It is a certain way, and therefore there has to be some necessary being that created it that way. This is therefore a continuation of the long process of history where science explains things up to a certain point, but where science has yet to come up with the theories religion fills in. Now, we do have some responses to the cosmic fine-tuning argument. Like I said, check out my series for more, but here's a few of them. So, First, we can simply say that this idea of a probability distribution for the laws of the universe is a poorly formed concept because we have no real information about the real range of possible values. It could be the fact that these constants are logically necessary instead of merely nomically necessary. And we simply do not yet understand the math and theories that are required to prove that. If this were the case, saying that life would be impossible if these constants were otherwise would be like saying life would be impossible if a statement could be both true and false at the same time, or if pi was even a slightly different value. Sure, that might be the case, but those things being any different are logically impossible. It's also possible that there is a probabilistic range for these values, but that range is actually quite small, or at least it's quite small compared to the number itself. And it's very likely that they would be what they are. In other words, even if a tolerance to allow for life is within a 10 to the negative 100, it could be that the actual range of possible values only varies by 10 to the negative 1000. Some of what's going on here is this confusion of probabilities of us observing something and the probabilities of something being a certain way. In other words, committing the metaphysical horse fallacy. We are putting the epistemic cart before the metaphysical horse. We are basing our probabilities on what we can know or what we can understand as opposed to what actually could be. Just because we can state a probability based on what we could observe doesn't mean that that's the actual probability of something being set, or that what that thing being set is actually based on a probability at all. A third key intuition here is that the proponents of the fine-tuning argument have not proven that it is a probabilistic process that sets those constants. In fact, such a process seems to violate things like the principle of sufficient reason, which argues that there must be a reason that the world is one way and not another. Things that have seemed truly random have always been found to have a deterministic cause. Those things that seem probabilistic right now are likely just the things we have not yet come up with a sufficient explanation for. This directs us to a fourth response to the fine-tuning argument, that we simply have not discovered the theory which explains all of these constants, which unites them all under a grand unified theory. Thinking anthropically, we are likely not to be at the end of science. And all of our previous scientific theories have been replaced, proven wrong and replaced with new paradigms. So it's unlikely that we actually have the right paradigm right now, especially given all of the unobservable entities we need to posit to make this paradigm work. A fifth response is once again this issue of life as we know it, simply because the kind of life that we have on Earth could not be sustained in a universe with fundamentally different constants. It doesn't imply that another universe with different constants would not sustain a fundamentally different kind of life, perhaps at a drastically different scale given the rate of expansion. We certainly can't do any empirical testing of how a universe with different constants could actually behave, so while we might speculate that they would not be compatible with our life, we don't know that for a fact if there are any other kinds of life that cannot live here but could live under different conditions. The sixth response is popular among cosmologists, and it is the claim that our universe is but one universe in a giant multiverse of universes. In the same way that it may be unlikely that the Earth can sustain life, but there are so many planets we don't find it impractical. One way to explain these constants is to say that there is a multiverse of many universes that have different constants. Many cannot sustain life, but some can. Next, we're going to dive into the multiverse. So, this is the possibility that there are many universes. It's important to note that there are a lot of different things that are perhaps isomorphically similar here in terms of that may be called the multiverse. We're going to touch on each of them and how they may correspond to the cosmological idea of the multiverse. So, first off, modality. This is the metaphysical idea of possible worlds. The idea of the multiverse is closely related to the philosophical concept of possible worlds, though they are distinct. In philosophy, possible worlds are what you are referring to when you say that something is possible or necessary. If you say something is possible, then it's true in at least one possible world. If you say something is necessary, then it's true in all possible worlds. For some, these are just imaginary. Modal combinatorialists claim that these are just different possible combinations and arrangements of things in the actual world. Modal fictionalists might argue that they're fictions that we're creating. For others, such as modal realists, these worlds are real, actual things. Modal realists claim that other possible worlds are real, but they're inaccessible from the actual world. And The actual world is just a designation that we give to our world, like other indexicals, here, now, I. There's nothing special about our world being the actual world, in the same way that here isn't a particularly special place other than it's the place that I am in right now. The actual world is just the world that we are in right now. The other possible worlds, for the people within those worlds, that world is the actual world to them. Now, for modal realists, there's something of a similarity between these possible worlds and the multiverse that we're talking about, but they're not quite the same. Possible universes, on the other hand, unlike possible worlds, are real physical places regardless of your theory, that may in principle be accessible from our universe, or may in fact have impacts on our universe. And some cosmologists argue that we can see the impacts of these possible worlds in things like the cosmic background radiation. However, a modal realist explanation of possible worlds would be sufficient to answer all of the questions of the fine-tuning argument, since all possible worlds actually do exist. So, possible universes can, at least in principle, be accessible from our universe, though because they are expanding away from each other very quickly under most of the theories, may not in reality be practically accessible from our universe. Whereas for the modal realist, possible worlds are in principle not accessible to us. But both of these theories address the question of the fine-tuning argument by saying there are many possible worlds that include, for the modal realist, all possible instances of what these particular constants could be, and therefore it's not unlikely that at least one of them would allow for life. Another adjacent and possibly interrelated concept is what is called the many worlds interpretation of quantum mechanics. Without digging into quantum theory too much, there are certain interactions of particles which appear to be truly probabilistic and non-deterministic. They exist as a field of probabilities until they're observed, at which point they collapse into a single outcome. The interpretation that the universe plays dice is not deterministic, and it's quite spooky and philosophically concerning for a range of reasons. So, one alternative theory that's positive to avoid this conclusion is the possibility of multiple worlds. This interpretation of quantum mechanics argues that in each situation and interaction where the wave function would be collapsed, the universe splits into many worlds, each where a different result took place based on the probability distribution of the event. Now, this raises all sorts of philosophical questions about identity. Are you the same as someone that took a different branch on the timeline, a different way down the trousers of time, as it were? About the nature of time, it's something that is splitting along all these cracks. Can we really be talking about something that happened in the past or something that happened at the same time but across another timeline? As well as possibility. Are these things that we should be using as possible worlds? Is this the true interpretation or better interpretation of possible worlds? Or is there something that's added by the philosophical interpretation, perhaps of the initial state of the universe, that would allow for more options in terms of possible worlds? But all of those questions will unfortunately need to await another video on quantum mechanics specifically. However, some have argued that this many worlds interpretation of quantum mechanics is an explanation for the multiverse used to explain fine-tuning. Basically, they argue that there was a point early in the universe where there was a true probability distribution of how certain universal constants could be set, and that this was one of the first branches of time. We branched into a bunch of different universes, possible branches, which had different universal constants. And sure, there are therefore multiple universes, some of which have fundamentally different constants. But it's not lucky that at least one universe like ours existed. It was in fact inevitable because all of those options are realized. The more common ones are realized more often, but all of the options are realized. There might be fewer universes like ours, explaining the apparent improbability of the certain placement of the cosmological constant, with constants that allow for life as we know it, but at least one was required since there is a world for all possibilities under this interpretation. But we might have some questions for this theory. It seems like we have not really posited a mechanism that particle interactions could in some way set the constants of the universe. This gets into the underlying concern that the likelihood of a particular constant being a certain way is a bit of a nonsensical question, as we don't know any way in which they could be different, because we don't know why they are that way in the first place. This points again towards the need for a paradigm shift in cosmology, or simply accepting that there are things that we don't understand. Some also argue that there are two separate types of multiverses: the cosmological multiverses that are simply distant from us in space, admittedly ever expanding space, while the quantum ones are distinct in some other dimension which we can't travel in, at least other than backwards up the branches of time, or fully independent, like the philosopher's possible worlds. So one might say that these are still importantly different from the multiverses the cosmologist is talking about. The cosmologist is talking about physically distant, admittedly very far, but physically distant universes within a similar multiverse. The quantum mechanist is talking about universes that exist along different branches of a timeline that are independent from each other. And the philosopher is talking about possible worlds that do not branch apart from each other, but have been independent and different from each other all along, and are in principle cannot interact with each other. So with that, let's dig in a little bit more to the cosmologist's type. A more common explanation of multiple universes for cosmologists is called eternal inflation. This expands on the idea we discussed with the Big Bang. Cosmologists think that there was a period of rapid, faster-than-light inflation in the past. This inflation slowed at a certain point to the normal dark energy level of expansion during the early in the universe's life. This theory of eternal inflation argues that this slowing might have been a local phenomenon, where just our area of the universe moved to a slower rate of expansion. This likely occurred at the same time in many areas of the overall universe, but because the space in between was expanding so much faster, by the time these universes were all created, they were pushed away from each other so fast that there was still more space than universe, and therefore that space was still expanding very quickly at this rate of inflation, and so it then proceeded to create more universes in that space, but the space that, because those universes were expanding slowly, they didn't take up as much space as the space in between them did. Space in between them pushes them further apart, and the process repeats. In other words, the Big Bang was just the beginning of our universe when it stopped inflating as rapidly, not at the beginning of the multiverse, which is creating new Big Bangs every second as the rest of space keeps inflating at this drastically rapid pace and pushing all these universes apart from each other. Now, these individual universes are often called bubble universes or pocket universes. Basically, they are a region where, for whatever reason, inflation has slowed substantially. Each is still expanding itself, but because it's expanding slower than the space between the universes, it's unlikely to ever cross over into another universe. Cosmologists theorize that these individual pocket universes could have their own different cosmological constants as they slowed from that different initial inflation at different rates, and they ended up at different rates of final expansion. While our bubble universe has a low cosmological constant that is required for life like ours to form, that's not surprising since there are incomprehensible many pocket universes that are being created every single second. So it's likely that at least one that looks like ours would form. Now, some have combined this theory, with the anthropic principle to argue for a solution to the Fermi paradox, sometimes called the Youngness paradox, in contrast. This relies on the fact that since the number of pocket universes is increasing exponentially, you can think of it like this: the amount of space we started with was less. A number of universes got created. Those universes got pushed apart because of inflation, and so now we have a bunch more space. Sure, we create universes in that space, but there's still some space left over. That space increases even more, and so each round there are more and more universes created. At any given moment, there are many more species that are the first intelligent life to be created in their universe than there are that are the second intelligent life to be created. Let's say, even imagining that there's the same rate of creation for any given set of intelligent life. Since it will take longer to get to the second type of life than the first, and there are so many more young pocket universes than older ones, we might imagine that universes in the first generation already have 3 or 4 types of life on different planets. But there are so many fewer of those universes than there are in the second generation that perhaps only have two types of life in existence. Or there are many fewer of those than there are in the third generation that perhaps have only one type of life. And so if we're saying which generation are we most likely to end up in, we're most likely to be in the third, because that's by far the largest. And so, or the most recent generation, which is by far the largest. And so we may think that there's a reason to think we are the first life to be created in a universe because we are more likely to be in a more recent situation. However, this is possibly unconvincing since it relies on this anthropic principle's weird treatment of probability and your own position within a probability distribution. It feels a little bit like the doomsday paradox, which is something we can get into in another video. Now, this is an especially speculative theory with little grounding in empirical evidence. Faster than light inflation has not been observed, just speculated about. So to speculate that this is not just something that happened at one point long ago in the past, like our standard model and the Big Bang Theory do, but rather that it is the primary state of the multiverse with no real empirical evidence, seems to stretch credulity to its breaking point. Now, some cosmologists argue that there is evidence for this interpretation in the cosmic background microwave radiation, in evidence of early pocket universes that might have formed next to our universe and therefore impacted the patterns of the background radiation. But at a certain point, one can find evidence for any theory by structuring it around the cosmic microwave background radiation and then building out from there. And so because it's our only observation we can base things on at a certain point, we start overfitting to that data set. We need to be able to do more experiments, which is inherently the problem of cosmology. Now, this brings us back to the central question of this video. Can cosmology really be considered a science? Perhaps some of the conclusions that we can draw about distant planets might at least seem quasi-scientific, but making suppositions about the multiverse seem wholly diverse from testable empirical science. That doesn't mean that it's not an interesting field to investigate or that we shouldn't investigate it, but rather that this might be better categorized as natural philosophy, the philosophy that we used before we had the scientific method, because we're not really testing any of these theories in a rigorous empirical way. Now, what is the danger of calling cosmology a science if it isn't quite one? Well, branding of the idea of science itself. If someone thinks that scientists are as confident about the multiverse as they are about the safety of vaccines, they might make choices that have real-world implications just because cosmologists aren't willing to admit that they have much less evidence or ability to test their theories than many other scientists do. So who knows? On the other side, perhaps the perception that science cannot answer all questions is a more dangerous view for the public to have of the field. And so cosmology, with its admittedly speculative answers to very deep and important questions, could actually improve the brand, on the other hand, when compared to other epistemic paradigms like religion, which claim to have answers to every question, even when they don't have strong evidence for them. So there's a question of this, but there's also a question of whether or not it can cut both ways. In the end, I'm a skeptic. I'm not certain that any of the claims of science are true. They seem more like good working theories given the evidence. To be science, if the evidence changed, the conclusion should necessarily change too. But that's the problem with cosmology. It's hard for the conclusions to change when the evidence we get is so infrequent and our ability to test the evidence is so limited. However, it does seem to me that science can be useful. Perhaps this is my issue with cosmology. There seems to be little use of it as a science, as more of an instrumentalist, where I don't necessarily believe science is true, but I think it's very useful for our daily lives. I struggle to see how cosmology, particularly this very speculative cosmology, is particularly useful for making everyday decisions or doing things. It is the realm of philosophy to speculate about questions we don't yet have the tools to answer. And cosmology seems to much more resemble those questions of philosophy than it does science. As speculative as the multiverse may be, it does seem to be a particularly powerful idea, given how often it shows up in literature, in media, in movies, in philosophy, and in science. Right? We just looked at three different, between the philosophical possible worlds, many worlds interpretation of quantum mechanics, and the multiverse theory of cosmology, three different disciplines within philosophy of science that have captured this idea of multiple worlds. It is everywhere in media and popular culture, this idea of another dimension or another world that you can step into and see how things would have been different if you chose things differently, or how things would have been different if the world were slightly tweaked in some way. Regardless of whether a multiverse exists, it is clearly an idea that humans are fascinated by imagining what might exist if things were different. To finish us off, we have questions of infinity. It's turtles all the way down. To infinity and beyond. Our last question to cover here is the universe infinite? So, many of these theories posit an actual infinity. Sometimes this is an infinity of empty space. Sometimes the universe itself is posited to be infinite. Sometimes it is the number of bubble universes that are created that are infinite. Sometimes it's the amount of time the universe has existed for or will exist for that are infinite. But this can be a challenge for a range of reasons. One is just a mental barrier. It's hard for a person to think about the important difference between a very, very, very large number, many of which we're working with in cosmology, and infinity. Many things in cosmology deal with unimaginably large numbers. Even distinguishing between these numbers and putting them into the context that a human can understand is very challenging, if not impossible. If something is very, very unlikely, humans often view it as impossible, even if there is a small chance it could happen. If there are so many instances of something, humans think that basically every possible combination must have occurred, even when these are not always perfectly true. However, even these very large numbers that are involved in cosmology all pale in comparison to infinity. If you do something an infinite number of times, all of the possible combinations will occur, no matter how unlikely they are. In fact, even the most unlikely outcome will occur an infinite number of times. This is hard to conceive of, and it leads to paradoxes. For example, if there are an infinite number of universes in a multiverse, not just unimaginably many, but truly infinite, then it is impossible for any universe to destroy the multiverse. It is impossible for there to be created a universe such that it destroys the multiverse. Since if it were possible, it would exist, and the multiverse would not, and everything would be destroyed. We wouldn't be here. This is why other versions of multiple worlds, such as modal realism, explicitly prescribe that interactions between the worlds are impossible. Because it's very easy to imagine. If it were logically possible that someone could move between possible worlds, then there would be a possible world where someone moves between possible worlds and can visit any world they want. And therefore, we should have been visited by someone from another possible world. Since we haven't been visited by someone from another possible world, it must be logically impossible, if modal realism is true, that no one can visit someone from another possible world. These interactions have to be inherently forbidden for some reason. Because if they aren't, infinity just runs wild and says, if it's at all possible, it happens somewhere. And if it happens somewhere and it's something that impacts everything or impacts other worlds, we should see evidence of it. Now, many cosmologists think that the universe is infinite. This is because they claim that there are three possible formulations of the universe. Positively curved universe, forming a hypersphere or a hypertorus. Imagine a situation where if you go far enough in any one direction, you eventually get back to where you started, like the screen of a video game that wraps around. I.e., if you head off in space in one direction, you go for many, 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 many light years, you will eventually come back to the same space you started. The universe could also be a flat space with no net positive or negative curvature, and therefore an infinite universe. Or it could be a negatively curved universe where parallel lines diverge, like a hypersaddle or a hyperpringle. Only a positively curved universe, hypersphere or hypertorus, where if you go off in one direction, you will eventually come back to that point, would be finite. All the others would be infinite. Now, based on cosmologists' current observations, it looks like lines of observation moving through space are parallel. In a positively curved universe that's finite, those lines going in space, parallel lines, would eventually converge and come together. If it's flat, they stay parallel, and if it's negatively curved, outwardly like a saddle, they would diverge. So scientists conclude that the universe is flat and infinite. However, we have a problem. We can only see a small part of the universe, and it's possible that the universe is very large, and the area we can see just appears flat in the same way that you cannot see the curvature of the Earth if you're standing on the ground. The ground looks flat, so you might assume that the Earth is flat, but the Earth is very, very big. If the universe is very, very big, it still could be finite, and we're just only picking up on the flat section here. Once again, this is getting back to the inherent problem of cosmology of assuming that everywhere is like the corner that we can see. Note that this is infinite in space, not necessarily in time. It appears that our universe had a beginning, the Big Bang. Though, as noted when discussing eternal inflation, we don't know if that was really the beginning of the multiverse or just our particular pocket universe. It is possible that the universe could continue on without end into the future and past, could have a clear ending, or could loop back on itself. But with any of these real infinities, there are paradoxes. Some philosophers have concerns with the idea of a real infinity. Not just an infinity for the purposes of mathematical calculations, but something that actually exists in the real world. There are lots of paradoxes that arrive from it. We'll look at one here. Hilbert's Hotel. So, Hilbert's Hotel is a paradox for the idea of a real physical infinity in the world, specifically some of these issues raised by cosmology. Imagine an infinite hotel that is full with an infinite number of rooms, each numbered 1, 2, 3, etc. Suddenly, an infinite number of new people show up, come into the hotel, and want to check in. Concierge says, "Don't worry, we aren't really full," and asks that each guest move to the room number that is double their current room number. Guest number 1 moves to room 2, 2 moves to room 4, 3 moves to room 6, etc. Every number has a number that's double its size, so every person has a new room. However, there are now also an infinite number of open rooms for the new guests to check into. An infinity plus an infinity still equals an infinity. If an infinite number of people checked out from all of the even-numbered rooms, then there would still be an infinite number of people in the hotel. But if an infinite number of people checked out from all but the first 2 rooms, there would not be. And so some people see a contradiction here, that infinity minus infinity in some situations is 2, but in other situations is still infinity. And in some situations could be 0, if an infinite number of people checked out from every single room. This seems to break some of our general understanding of the way numbers should work. Hilbert argues that this shows that a real infinity cannot exist, because he claims that if such did, then the events described in the hotel would be possible, but they are absurd, so such an infinity cannot exist. Therefore, the universe cannot be infinite. Many cosmologists are not convinced by this experiment. In fact, this exact situation is what is being described in the Big Bang, by people moving to rooms that are twice their original number. We had an infinitely large universe that is getting less dense. It's exactly what we see with space expanding rapidly in between matter. It's just like everyone moving to the even-numbered rooms. We still have an infinite amount of stuff, it's just further apart. In fact, this is a pretty good parallel for what we expect the universe to doing, except they do keep moving for the universe. First to even-numbered rooms, then to multiples of 4, then to multiples of 8. They get further and further apart the more the universe expands, but there's still an infinite number of people in there, even if there's progressively being more space in between them. I'm not convinced that Hilbert has truly given us a reason to be skeptical of real infinities, because I don't quite see the contradiction here. Infinity has certain properties that other numbers don't have. Infinity may have weird counterintuitive properties that we might be slightly uncomfortable with, but I don't see that it has necessarily a contradiction, a logical contradiction here that's being created, because explicitly infinity is different than other numbers and it doesn't follow the same rules. Now, there are many other paradoxes of infinity, some of which directly apply to the question of real universe infinities, some of which have more to do with time and space. Check out our videos on the Thomson's lamp paradox, Cantor's paradox, and the Littlewood-Ross paradox, and of course, Zeno's paradoxes for more on all of this. As a skeptic, my issue with a real infinity is not that it's inherently impossible, but that we cannot know its properties or even if it exists. How would we be able to determine whether something was very large or actually infinite? When comparing the closed hypersphere model of the universe, for example, with an infinite flat universe, we might be able to show that the universe was positively curved, i.e., if we were able to prove that it was a sphere, go all the way around from one direction, you will end up in the same place, we could prove that. Or we could say that it is a positively curved hypersphere if it is very large, but we cannot say that it is certainly infinite. Think of it this way. As we get more and more universe in our observed radius, we can see further and further, and we can understand more and more about how the universe is behaving within that area. As it gets bigger, if we continue to see it as flat, then we either can say the situation is either that the whole universe is flat or that the universe is finite, but the patch that we're on is larger and larger. Another way to think of this is think of yourself rising off of the surface of the Earth. When you're standing on the surface of the Earth, you can't tell if the Earth is flat or if it's round. But the further up you go, the more you can see the curvature of the Earth, and the more you can see that. If you keep going up and up and up, and the Earth still seems flat and flat and flat, then it's more and more likely that the Earth is flat, but you can never be sure because you can't be sure that the Earth isn't really, really, really big. It's the same with the universe. We can never be certain that it's actually infinite because the best we can do is say, well, if it wasn't infinite, it would be this big, or it could be infinite. We might be able to exclude small closed universes, but we can't affirmatively prove a infinite universe, whether it be flat or saddle-shaped. With that, here is the map of the philosophy of outer space. Thank you for joining us and watching these videos. Watch this video and more here at Carneades.org, and stay skeptical, everybody.